In the previous video, we saw that the number of 3-element subsets of a set with 4 elements, this number can be computed by this formula, and that the answer is 4. So now, in this video, I want to explain why this formula is correct. So the first thing we need to establish to see why this is correct is that this is equal to P43 over 3 factorial. Remember, P43 is the number of permutations of length 3 where the symbols are chosen from an alphabet with 4 different symbols. And we have a formula for this. P43 is equal to 4 factorial over 4 minus 3 factorial. So if we divide both sides by 3 factorial, then we can use division to figure this out. So remember, 3 factorial we can think of as 3 factorial over 1. Then this is the same as saying 4 factorial over 4 minus 3 factorial divided by 3 factorial over 1. Now remember, with division, we flip and multiply. So we have 4 factorial, 4 minus 3 factorial times 1 over 3 factorial. And this gives us 4 factorial, 3 factorial, 4 minus 3 factorial. And so you could see that that's equal to that. So in fact, what we just showed is through a string of equalities that this is equal to that. Equals goes both ways, so we know, in fact, that they are equal. So now we want to think about what does C43 count and what does P43 count. Remember that, like I said before, P43 counts the number of permutations of length 3 where the symbols are chosen from an alphabet with 4 symbols. So now let's specify an alphabet with 4 symbols. So the alphabet that we'll use for this example is W, X, Y, Z. And so if this is our alphabet of symbols and we're going to count the number of permutations of length 3 where the symbols are chosen from here. If I was to write out all of these permutations of length 3 where the symbols are chosen from this set here, from this alphabet, these would be all of those permutations. This is all of them. And now here at the bottom, we have all of the 3-element subsets of the set W, X, Y, Z. All right, and now as you can see, there are many more permutations of length 3 chosen from this alphabet than there are subsets, 3-element subsets of this alphabet, W, X, Y, and Z. And so let's think about, first of all, why is there more? Well, the reason that there's more is because in permutations, order matters. Order matters. So what does that mean? So as an example, let's look at these first 2 in the upper left corner, these 2 right here. Because order matters in permutations, X, Y, Z is considered to be different than X, Z, Y. But with combinations or subsets, with sets, order does not matter. Order no matter. So if we were to think of xyz and xzy as sets, then this would be the set x, y, z, and this would be the set x, z, y. And notice that, in fact, that both of these are equal to that set right there. Remember, two sets are equal if they have the same elements. Order does not matter in sets. So when we use P43 to count C43, we overcount by a factor of 6. This is because each of these 6 permutations counts this one 3-element subset. This is because these 6 permutations count that subset. And these 6 permutations count that one. And these 6 permutations count that 3-element subset. This is because all of the things in the blue box, when thought of as permutations, order matters. So they're all different in P43. But if you think of them as 3-element subsets or 3-element sets, they're exactly the same thing. So to C43, they're all the same thing. And so in each of these boxes overcounts the set that they're pointing to by a factor of 6. Now, where does this 6 come from? All right, so just looking at these 6 permutations here, notice that we can think of these 6 permutations. Oh man, blast. Notice that we can think of these 6 permutations as permutations of length 3 chosen from the alphabet XYZ. All right, so to recap, we can think of each of these permutations of length 3 as permutations of length 3 chosen from the alphabet XYZ. And we can think of each of these as permutations of length 3 chosen from the alphabet WYZ. And we can think of each of these as permutations of length 3 chosen from the alphabet WXZ. And we can think of each of these as permutations of length 3 chosen from the alphabet WXY. And so now remember, how many permutations of length 3 are there when you have 3 distinct symbols to choose from? There are 3 factorial. So there are 3 factorial which equals 3 times 2 times 1, or 6 of these. And similarly, there are 3 factorial of these, 3 factorial of these, 3 factorial of these. So when we say that we overcount each of these by a factor of 6, what we're really saying is we overcount each of these by a factor of 3 factorial. So this is why P43, which we know is 24, which is equal to 6 times 4, or 3 factorial times 4. This is why P43 overcounts C43 by a factor of 3 factorial. And so now with this in mind, right, with this in mind, we can see that P43 which we know is 3 factorial times 4, divided by 3 factorial equals 4, which is C43.